In this video, we explore electron configurations and orbital diagrams in a bit more detail and show how both are closely linked to the structure of the periodic table. So here is the orbital diagram for multi-electron atoms that we can use in combination with the Aufbau Principle and Hund's rule to construct orbital diagrams and full electron configurations for all atoms. For example, to generate the orbital diagram and electron configuration for the sodium atom, which has an atomic number of 11 and therefore 11 electrons in its electron cloud, we start by filling the 1s subshell with 2 electrons, spin paired, then the 2s subshell with 2 electrons, spin paired, then the 2p subshell, in order, according to Hund's rule, placing single electrons in separate orbitals with parallel spin before spin pairing, and then finally placing the 11th electron into the 3s subshell. This gives the electron configuration for sodium as 1s2, 2s2, 2p6, 3s1, and a condensed electron configuration of the neon core of 10 electrons plus the 11th 3s electron, so neon core 3s1. What we are able to show is that the successive filling of subshells using the Aufbau principle matches the structure of the periodic table, and that the filling of S, P, D, and F subshells corresponds to elements in the S, P, D, and F blocks of the periodic table. In other words, orbital diagrams and electron configurations appear to be different ways of representing the structure of the periodic table. Let's examine this idea a bit more closely as we fill successive subshells in the orbital diagram for multi-electron atoms. We'll start with the first electron, which represents hydrogen with an electron configuration of 1s1. Adding a second electron results in the orbital diagram for helium with an electron configuration of 1s2. The first thing to note about the filling of the 1s subshell is that when it is full, that is with 2 electrons, we have a very stable electron configuration. How do we know that? Well, we know that helium is very stable and tends not to take part in chemical reactions, which means it has a very stable electron cloud. And it turns out that that stability is associated with the fact that the 1s subshell, and indeed the n equals 1 shell, is full. Stable electron clouds are associated with full shells and full subshells. The second thing to note about the filling of the n equals 1 shell is that only 2 electrons can fit in this single orbital corresponding to the elements hydrogen and helium. When we look at the periodic table, we note that in period 1, there are only 2 elements, hydrogen and helium. If we go back to our orbital diagram and start filling the n equals 2 shell, we do so by placing electrons in the 2s subshell, corresponding firstly to lithium and secondly to beryllium. And then we continue to place electrons into the next available subshell, the 2p subshell, representing the elements boron, carbon, nitrogen, oxygen, fluorine, and neon. And again, we note that the orbital diagram and electron configuration for the noble gas neon has a full shell and full subshells. Neon, as I said, is a noble gas. It is very stable and tends not to form compounds or be involved in chemical reactions due to an inherently stable electron cloud. So again, we see the link between full shells and full subshells with stable electron configurations. The other thing to note is that these 8 elements here correspond to the filling of the 2s and 2p subshells within the n equals 2 shell. If we have another look at the periodic table, we see that period 2 has 8 elements in it in total, 2 of them in the s block and 6 of them in the p block. So it seems that the n equals 2 shell, which accommodates 8 electrons, corresponds to period 2 in the periodic table, which has 8 elements, and that these 2 elements here in the s block correspond to the 2 electrons allowed in the 2s subshell, and that these 6 elements here in the p block correspond to the 6 electrons allowed in the 2p subshell. And we can keep going with our filling of the orbital diagram and get to the n equals 3 shell, 11 electrons, representing sodium with the neon core in the 3s1 electron, 12 electrons, representing magnesium with the neon core and the 2 3s2 electrons, followed by aluminium, silicon, phosphorus, sulfur, chlorine, and argon. And again, we see that filled subshells are associated with stability, as we know that argon is a noble gas with a stable electron cloud resulting from the filled 3s and 3p subshells. And again, we note that the filling of the 3s and 3p subshell within the n equals 3 shell corresponds to these 8 elements. And if we have another look at the periodic table, we see that period 3 also has 8 elements in total, with 2 in the S block and 6 in the P block. So it seems that the n=3 shell that accommodates 8 electrons corresponds to period 3 in the periodic table, which has 8 elements, and that these 2 elements here in the S block correspond to the 2 electrons allowed in the 3s subshell, and that these 6 elements here in the P block correspond to the 6 electrons allowed in the 3p subshell. We'll keep filling for one more level and start filling the 4s subshell with a 19th electron, giving us the orbital diagram and electron configuration for potassium, atomic number 19, with the argon core of electrons plus the additional 4s electron. A 20th electron gives us calcium, atomic number 20, with the argon core of electrons plus the additional 4s2 electrons. These two elements, potassium and calcium, start the 4th period of the periodic table, and they have electron configurations of an argon core plus the 4s1 and 4s2 electrons respectively. In other words, they have s orbitals filling in their highest energy orbitals. And that is why we call these groups 1 and 2, the s block, because all of the elements in this s block have s subshells or s orbitals filling up as their highest energy orbitals. The next subshell that we start filling after the 4s subshell is the 3d subshell, corresponding to elements 21 through 30 in the so-called d block. Going back to our orbital diagram, we see that the 3d subshell is the next to fill, and it can accommodate a total of 10 electrons, corresponding to the 10 elements in the d block, from scandium to zinc. After the 3d subshell, the next subshell to fill is the 4p subshell, which can accommodate 6 electrons, corresponding to these 6 elements from the p block. And yet again, we note the link between the noble gas configuration of krypton and the filled shells and filled subshells from n=1 up to n=4. And we also note that these 18 electrons in the 4s, 3d, and 4p subshells correspond to these 2 elements in the s block, and these 10 elements in the d block, and these 6 elements in the p block, for a total of 18 elements in period 4. So, what we see is that the S, P, D, and F blocks of the periodic table correspond exactly to the subshell designations in orbital diagrams and electron configurations. And we can even break up these blocks into subblocks, including 1s, 2s, 3s, 4s, etc., and then 2p, 3p, 4p, 5p, etc., and 3d, 4d, 5d, etc., and finally 4f and 5f. Given that orbital diagrams and electron configurations are actually different ways of representing the periodic table, we will see in subsequent videos how the periodic table can be used to generate electron configurations, and therefore how we can predict many chemical and physical properties of elements based on their position in the periodic table.